Hi, welcome to the talk. Solar geoengineering, also called solar radiation modification, is 14 times stronger than CO2 mitigation. This is part one of two. So, I'm Dr. Alec Feinberg from DR Farsoft Research out of Northeastern University. You can get my bio and papers I've written here, and you can shoot me an email if you have any questions. Okay, now this particular part one provides fundamental values and numbers that anybody who's involved in mitigation or in climatology should know about. Probably this paper should have been written about 15 years ago, especially part one here, so we understand things a lot better, and maybe things would be a little bit different in how we're approaching things. This talk is based on this preprint right here, and the status is currently submitted to a journal, and again, my bio here. Okay, so part one and two is related to this paper. So in the introduction here, as I mentioned, part one will be on mitigation, forcing efficiencies, and we'll talk about this 14x factor, which is a basic upper limit, a fundamental number that we should know about. And then we'll talk about solar geoengineering versus greenhouse gas removal, solar forcing as well. And we'll get into some background climate amplification estimates that are fundamental, also that people should know about. We'll talk a little bit about urbanization, the albedo decline on the planet, and a little bit of annual solar geoengineering, which will be explained a lot more in part two. Now, part two has the same main title, and the subtitle is what we'll be talking about is basically IPC CO2 estimates are too high. We'll look at the albedo decline, which should be included, and we can see that from a simple model, and that's how we know. So hang in there for part one is pretty simple. Part two is a little more complicated, but both parts you should know, and we'll get into more details on annual solar geoengineering. Okay, so in part one, we're going to make a mitigation comparison on solar geoengineering versus CO2 removal. We'll also talk about solar forcing versus CO2 increases. All right, the first part we need to know is that the Earth's energy budget and some literature information. So greenhouse gases amplify the solar warming provided by the sun by about 62% increase. So this is like you can think of it as an amplification estimate. So, and this is explained in more detail in part two. I'll show you an energy budget model there. And it brings the temperature of the Earth up to about 15 degrees C. So we know it's about 62%. And the greenhouse gases consist of water vapor, clouds, CO2, and other greenhouse gases. And their proportions, the main one that we're concerned about in this talk is the CO2, and that's 19%. And we're going to show a lot of the information from that. And the other greenhouse gases about 7%. So of the CO2 contributions, this 19% of the 62% is the greenhouse gas effect. So the contributions from CO2 we can think of is about 0.19 times the 62%, or about 11.8% warming effect from just the CO2 greenhouse gas. All right, let's look at mitigation and try to understand solar geoengineering versus CO2 mitigation and how we get this fundamental 14 value number. Now, when the solar radiation comes in from the sun, it passes right through the greenhouse gas because it's light, and the greenhouse gases aren't affected by the solar light coming in from the sun. Now, when it hits a hot spot like a black asphalt surface, it heats up and causes warming, as we know. And we're going to use 1 watt per meter squared as a nice number. So we're going to say the surface is heated by 1 watt per meter squared. Now what happens is next is that the greenhouse gases will amplify that, as I mentioned, about 62%. And so the actual effect, if we were to do cooling, to mitigate that hot spot, so we're going to cool that hot spot by having a highly reflective surface. We're going to take that black asphalt road and make a cool surface and make it reflective. We would get a 1.62 solar geoengineering mitigation. So even though we only remove 1 watt per meter squared of heating on the surface, the total greenhouse gas cooling will be 1.62. So now that is also a fundamental number that all climatologists should understand. Now, what happens if we decide to do mitigation just by removing CO2? Well, we know the only effect that we will get is a cooling based on its portion of the greenhouse gas, which is 0.192 times 0.62, and we're going to look at that. So notice that when we remove the CO2, what happens is that we get some cooling, and but the other greenhouse gases remain, so a good portion of it still gets re-radiated. As well, when you mitigate CO2, it doesn't do anything to the hotspot absorption. So now let's make some comparisons. So let's look at the cooling forcing, what I call the efficiency. So you can think of it as being stronger or weaker, or efficiency. So the proper term would actually be efficiency. So we said that solar geoengineering per watt per meter squared, the total effect is a cooling of 1.62, not just the 1 watt. So the work that we have to do is a cooling of 1 watt per meter squared, but with the total cooling that we get is this extra 0.62. Now, when we do cooling by carbon dioxide removal, the 1 watt per meter squared, what we get is only that portion of the greenhouse gases, which is 0.19 times that. So that's a 0.118 watt per meter squared effect on the surface. So the actual ratio comes out to be, for the efficiency, about a factor of 14, which is the title of the talk. And this is another fundamental numbers. So these numbers are fundamental values per watt per meter squared. So you get an estimate of what is actually happening. So this guy is 14 times more efficient than that. So you have to really remove a lot of CO2 to actually get a strong effect. This is why we should understand that solar geoengineering is a much more powerful way to mitigate the climate system. So in summary, when we mitigate down here, I also looked at the perturbation for the climate, and I added that in. So that, when I say perturbation, because we have forcing today, which means that we have a extra warming, it takes away from the natural greenhouse gas energy budget system a little bit. So that drops down to about 12.6 to 14 range. And if we just did a general removal of greenhouse gases, solar geoengineering would, this number would be 0.62 on the bottom. If we did greenhouse gas removal, not just CO2, a lot of greenhouse gases, then we would get a 2.6 number that solar geoengineering would be also stronger. Now, notice that I didn't mention it, but we should realize that it's not just solar geoengineering, it's also solar forcing. So solar forcing would be a factor of 14 times higher than CO2 forcing. So we have to be careful what we do to our planet when we darken it. And that's the next thing I'd like to talk about. So in terms of governance implications, solar geoengineering should be considered a premier mitigation tool. Urban albedo management, such as roads, roofs, and vehicles and building sites, remains underregulated, because now we know that solar forcing is also a big deal. And so we have to be careful about how we darken the planet, and this goes along with not just when we do forcing on our cities by black surfaces, but when we get feedback like snow and ice melting and we decrease the albedo of the planet, that will be 14 times worse than in the than the CO2. Now, in the Paris Accord, we should expand that to include explicitly albedo goals. The Arctic region is a very needed area where albedo protection is especially urgent. So we need to know that albedo preservation should be as at least a primary goal along with CO2 uh, uh, reduction. So we need to know that in order to do proper governance. So it's just as important, if not more so, that we be worried about albedo preservation. Now, I'd like to talk a little bit about the background, climate amplification, so we can see what's going on when we darken surfaces. Now, we talked about a 1 watt per meter squared darkening of the Earth. So when that heats up, the actual effect will be from the greenhouse gas trappings, we will get an extra 1.62. So this is an albedo greenhouse gas surface effect. And that is what's called a forcing. Now, it's not at the top of the atmosphere, but it certainly contributes. And we actually live in the troposphere. So we have to be mindful that we live on the surface, and we need to not just say, well, it's very hard to see these things at the top of the atmosphere where climatologists are concerned about forcing, and they really can't see what's happening in cities. Now, on top of that 1.62, which is really an amplification factor also, we get feedback. Now in 2025, the amplification feedback factor is about 2.2. So a lot of climatologists work on feedback. They use the units of watts per meter squared per degree C. You can easily convert this amplification factor used for the climatologist people using the Planck factor. It's a very linear effect. So now on urban heat islands, we also get an amplification factor of about 2.3 because urban heat islands also have some trapping of light. Just like greenhouse gassing do some trapping. There's a lot of effects in windows in urban heat islands. Tall buildings have a very large surface area, and these sort of things can't be seen from satellites, which have underplayed the amount of warming that urban heat islands are causing. And I talk about alternate studies that are recent, and myself also provided an alternative study that shows that urban heat islands are contributing to global warming, and the alternate study showed about 12 to 13% effect. So the total amplification, if you do a warming, especially in an urban heat island of a hotspot, you can get that 1.62 kick from the albedo greenhouse gas. So this is a surface greenhouse gas interaction effect. You get a feedback effect because we have water vapor increasing in the planet and snow and ice melting and other feedbacks that are occurring. If you're not familiar with feedback, you can look it up on YouTube. And it's very common. There's a lot written about it. Also, in the urban heat islands, the heat expands beyond the city limits, so we know it's causing amplification. So the actual number can kick up to 8.2 watts per meter squared just from a 1 watt per meter squared warming in cities. So this is why when you do estimations of urbanization, why a lot of people need to know that we need to do ground-based studies. We can't see this kind of thing from the top of the atmosphere and using satellite studies. Okay, now you have an idea of what happens when we darken the planet, and that's a very bad issue. So I want people to be aware of that, and so we need to immediately start banning black roads and banning black surfaces in the Paris Accord, and that has to be added to it. These are very important fundamental numbers, values, or at least these are our background numbers, the 1.62 and the 2.2, the 2025 number for feedback, and this added number for urban heat islands. So we have rural estimations as well as urban heat island issues. Okay, so in conclusion, solar geoengineering and solar forcing is 14 times more efficient than CO2 changes on an equivalent energy basis. The Earth responds more strongly to short wavelength reflection, or these albedo, which is a reflectivity of the planet, than to long wave absorption. Remember that the sun comes in is the primary warming of the planet. The greenhouse gases are a secondary effect. So the sun is on the front end, and we can do much more mitigation on the front end than on the back end. Okay, and I want to remind people to see part 2, and this is what part 2 will look like. So check that out. And I want to thank you for listening to part 1. And in part 2, we're going to talk about how we could mitigate using annual solar geoengineering, which is a much more mild method and should help in governance. All right, thank you very much for listening.